Welcome back. Today, we're diving into the fascinating world of cyclic hydrocarbons. When carbon atoms form rings, their geometry changes everything from their stability to how they interact with other molecules. Let's break down the geometry of rings. In cycloalkane ring strain and shapes. First, let's look at the smaller rings: cyclopropane, cyclobutane, and cyclopentane. In organic chemistry, carbon prefers an ideal bond angle of 109.5 degrees. However, in cyclopropane, those carbons are forced into a tight triangle with 60 degrees angles. This creates high-angle strain, making the molecule highly reactive because those bonds are practically screaming to pop open. Plus, the hydrogen atoms are eclipsed, adding even more tension. As we move to cyclobutane, the angle increases to about 88 degrees. To relieve some stress, the ring isn't a flat square, it puckers to reduce hydrogen eclipsing. By the time we reach cyclopentane, the angles are at 104.4 degrees, much closer to that ideal tetrahedral shape. It adopts an envelope conformation, where the atoms stagger themselves to keep the energy low. To understand why some chemical rings are more reactive than others, we have to look at ring strain. Think of it like a mechanical spring being forced into a shape it doesn't want to hold. Let's see the ideal versus the forced angle. In a standard carbon chain, atoms prefer a relaxed, tetrahedral bond angle of 109.5 degrees. However, in cyclopropane, the three carbons are locked into an equilateral triangle. This forces the bond angles down to just 60 degrees. This extreme compression, a massive 90.5 degrees deviation from the ideal, creates intense angle strain. It's like pulling a spring tight. The molecule is under constant internal pressure to snap open. Torsional strain and energy. The instability doesn't stop at the angles. Because the cyclopropane ring is planar, or flat, the hydrogen atoms are forced into an eclipsed position. They sit directly behind one another, creating torsional strain. If you look at the potential energy graph, you'll see cyclopropane sits at a high energy state. This makes it exceptionally uncomfortable and highly reactive. To minimize this energy, the bonds actually bend slightly outward, but the molecule remains a high-tension loop of nature. In short, small rings equal high pressure. The combination of forced angles and crowded hydrogens makes cyclopropane the pressure cooker of organic chemistry. In the world of organic chemistry, cyclohexane is known as the king of rings because of its extraordinary stability. But what makes it so special? Let's look at how it avoids the stress that smaller rings face. The problem is stressed flat hexagon. If cyclohexane were a flat, 2D hexagon, it would be in trouble. A flat shape forces the bond angles away from their ideal state, creating angle strain. Even worse, all the hydrogen atoms would be eclipsed, sitting directly behind one another, causing high torsional strain. This flat version is high energy, unstable, and highly stressed. Hers is the solution, the chair conformation. To find relief, cyclohexane folds into a 3D shape called the chair conformation. This is nature's Goldilocks solution. It's a perfect fit. First, it restores the bond angles to a near-perfect 109.5 degrees, eliminating angle strain. Second, it staggers all the hydrogen atoms, meaning they stay out of each other's way. This results in the lowest potential energy, making the molecule incredibly stable. Let's see axial versus equatorial positions. In this chair shape, the hydrogen atoms occupy two distinct positions. In axial positions, these point straight up or down, like the vertical axis of the Earth. In equatorial positions, these point outward, along the equator of the ring. Understanding these positions is the secret to predicting how larger groups will attach to the ring without causing new stress. By simply changing its shape from a flat hexagon to a 3D chair, cyclohexane eliminates all internal strain. It's the ultimate example of how geometry dictates stability in chemistry. Think of molecules not as static drawings, but as dynamic, moving objects. Take cyclohexane. It doesn't just sit still, it constantly flexes through a process we call a ring flip. In chair conformation, a look at the first chair on the left. We have a methyl group sitting in an axial position pointing straight up. Notice those red tension lines? That's because the bulky methyl group is physically bumping into its neighboring hydrogen atoms. This is a high-energy, cramped situation called a 1,3 diaxial interaction. It's like trying to sit on a crowded bus with a giant backpack on your lap. It's uncomfortable and unstable. In the boat transition state, to fix this, the molecule flexes. The footrest of the chair moves up, and the headrest moves down. For a brief moment, it passes through this boat transition state. As you can see on the energy graph, this is the peak of the hill. It takes a bit of energy to get through this crowded middle phase. In chair conformation B, finally, the flip is complete. Look at the chair on the right. Our methyl group has moved from axial to an equatorial position, pointing out toward the equator of the ring. The result: suddenly, there's plenty of room. The methyl group is spatially free, the tension is gone, and the molecule is now in its lowest energy state. The big lesson here is nature is efficient. Bulky groups will always prefer the equatorial position to avoid those 1,3 diaxial interactions. Remember, axial is crowded, equatorial is comfortable. By flipping, the molecule finds its perfect balance. Let's see the concept of the ring barrier in open-chain alkanes. Atoms can spin freely around their bonds. But when carbons form a ring, they create a C-C bond barrier. This rigid structure prevents free rotation, locking atoms into specific spatial arrangements. This leads us to a fascinating concept called geometric isomerism. Cis 1,2-dimethylcyclopentane. Look at the molecule on the left. This is the cis isomer. Notice how both methyl groups, the orange spheres, are pointing in the same direction. In our drawing, they are both up. Because these bulky groups are on the same side, they can crowd each other, leading to a high energy and stressed state, as shown by the red gauge. Trans 1,2-dimethylcyclopentane. Now, look at the right side. This is the trans isomer. Here, the substituents are on opposite sides. One is pointing up, represented by a solid wedge, and the other is pointing down, represented by a dashed line. By staying on opposite sides, they stay out of each other's way. This results in the lowest potential energy and a much more stable molecule, indicated by the green gauge. Why it matters? It's important to remember, cis and trans are not just different ways to draw the same thing. Because of that rotation barrier, they are entirely different molecules. They have different melting points, boiling points, and chemical behaviors. We've explored the individual pieces, but how does it all come together? As we can see, the geometry of the ring doesn't just look interesting, it dictates exactly how molecules behave in the real world. The stability hierarchy on the left, we see the cycloalkane stability hierarchy. It's a clear progression, from the high strain, tension of cyclopropane, through the intermediate strain of larger rings, down to the lowest strain of the cyclohexane chair. This hierarchy is nature's way of seeking the path of least resistance. Steroids, nature's elaborate rings in the center. We see this theory in action within a steroid molecule. Notice the fused rings labeled A, B, C, and D. These aren't just random loops. They are a series of interconnected chairs. These fused rings create a rigid, stable backbone that allows complex molecules, like hormones and cholesterol, to maintain their shape and function within our bodies. Stereochemistry and biological docking on the right, we see why cis versus trans matters so much. A small flip in spatial arrangement completely changes the shape of the molecule. This determines how a steroid docks into a biological receptor. As you can see, the trans steroid fits differently than the cis steroid. In biology, shape is everything. If the key doesn't fit the lock, the chemical message isn't sent. So, understanding cycloalkanes is about understanding stability in space. From the elegant stability of the chair to the complex architecture of human biology, the 3D logic of these rings defines the very function of life's molecules. Keep practicing these spatial relationships, and you'll master the language of organic chemistry. If you found this helpful, don't forget to like and subscribe for more deep dives into the molecular world. See you in next video. Happy learning chemistry with Harshada.